We have seen how to calculate the rank of a matrix, how to calculate the inverse of a matrix, then we have seen how to calculate eigenvalues and eigenvectors of a matrix. So, today we will be talking about certain what I call special matrices, okay, and the kinds of matrices that we will be talking about are symmetric, orthogonal, Hermitian and unitary matrices. Okay. So, let us start with symmetric matrices, and again as we have been doing earlier, we will restrict to square matrices only. Okay. So, if you have a square matrix, so let us say A, which is composed of the usual coefficients which we denote as Aij. Okay. This is our usual matrix which we have been using. So, you have A11, A12 up to A1n, A21, A22 up to A2n, AN1, AN2 up to ANN. So, this is our n by n matrix. Now, this matrix is said to be symmetric if the off diagonal elements, if any two off diagonal elements are identical. So, if A21, is the same as A12, okay, and so on for all the off diagonal elements. So, that means AN1 will be the same as A1n and so on. So, if all the sets of off diagonal elements are basically the same, okay, then we say that the matrix is symmetric. So, mathematically we can write this in two ways. So, if Aji equal to Aij, okay, then A is symmetric. Okay. So, if the ij and the jith element are identical, then the matrix is said to be symmetric. Okay. Now, there is another way to write this. Okay. You can also write this as A transpose is equal to A. So, A transpose, remember A transpose is the same as A with the off diagonal element swap. So, A transpose has A12 here instead of A21 and so on. So, these are basically the same thing. So, a matrix is said to be symmetric if either you can say A transpose equal to A, or if you want to look at the individual coefficients, you can say Aji equal to Aij. So, what will a symmetric matrix look like? So it will look like something like, so all the diagonal elements will be as you always had. Now, the off diagonal elements, so if this is A12, this will also be A12. If this is A13, this will also be A13, and if this is A1n, this will also be A1n. So, all the off diagonal elements will be identical to each other, and the matrix will have the appearance of symmetry. So, it will look very similar across all these. So, similarly, I should also mention here, so if you have A23, okay, this will also be A23. Okay. So, both these will be A23 and so on. So, symmetric matrix is one kind of special matrix. The next kind of special matrix is what is called as orthogonal matrix. Okay. And let us just remind ourselves. So, for a symmetric matrix we had A transpose equal to A. Okay. Now, an orthogonal matrix is we can write this in two different ways. An orthogonal matrix, usually we think of an orthogonal matrix if you can, I will say that a matrix is orthogonal if it preserves the length of a vector during a transformation. So, it is very important. So, suppose you had A matrix and it operates on a vector x to give you y, okay, then A is said to be orthogonal if the norm of x is equal to the norm of y. Okay, so then the length of these vectors is preserved after the transformation. Okay, then we say that A is orthogonal. Okay, it should be for all vectors. So, for any vector, when a matrix acts on any vector, it preserves the length of that vector, then such a matrix is said to be orthogonal. Okay. Now, what are the conditions for orthogonality? Can we find some conditions in the coefficients? And yes, we can do that. So, if I just take norm of y, okay, so this will be norm of Ax, okay, and the norm of Ax I can write as I can write A times x as various elements. So, the elements will be A 1j xj sum over j, and then you will have sum over j A 2j and so on all the way up to sum over j A nj xj. So, this will look like a vector. So, Ax will look like a vector where these are the components by usual matrix multiplication. Okay. So, if you use usual matrix multiplication, these are the components of Ax. So, the norm can be calculated as the sum of squares of each of these components. So, I can write the norm as in the following way. So, I can write the norm as sum over, I will just use an index k equal to 1 to n. Okay. And what I will do is this is a kth row. So, I will write this as sum over j equal to 1 to n A kj xj, and this whole thing has to be squared. This entire thing has to be under the square root. So, this is the norm of the vector. Okay. And now what you are doing is, so you are squaring a sum means you are multiplying this sum by itself. Okay. And it is not hard to see that this will turn out to look something like this. Okay. So, I will just write norm of y square. Okay. So, this will look like sum over k equal to 1 to n. Okay. Now this is a, you have one sum and you are squaring it. Okay. So, when you square a sum of terms, okay, then it is like making a double sum. So, what I will write this as sum over, instead of j I will write okay, I will write j equal to 1 to n sum over L equal to 1 to n. Okay. And what I have is, I have A kj A kl xj xl. Okay. So, this is exactly the square which I wrote in this form. So, now what this implies is that now this should be exactly equal to sum over xj square, right. So, if this has to be an orthogonal matrix, this whole thing should be exactly equal to sum over xj square. Okay. And so, what that implies is that this sum over k, so if I change the order of the sums, what I will get is sum over j equal to 1 to n sum over L equal to 1 to n. Okay. And what I have is I will have an xj xl, and then I have a sum over k equal to 1 to n A kj A kl. Okay. Now, if this matrix A has to be orthogonal, then the norm of y square has to be the same as norm of x square. Okay. And so, if A is orthogonal, then you can immediately write that you should have the condition norm of x square should be equal to norm of y square. okay. And now if you use this expression for norm of y square, you know that norm of x square is nothing but sum over I will use the index j equal to 1 to n xj xj. I will just write, instead of writing xj square, I am just writing it as xj xj. Okay, so this is what you mean by the squared norm of x, and this should be identical to what we have here is you have a sum over j equal to 1 to n, and additionally you have a sum over L equal to 1 to n xj, and you do not have xj into xj, you have xj into xl, and not only that, you have this additional term which looks like sum over k equal to 1 to n akj akl. Okay. Now you can just take a look at this, you immediately realize that in order for this to be true, okay, what should happen is that this whole thing here, this whole thing, okay, should be such that it should be 1 if j equal to L and it should be 0 otherwise. Okay. So, in other words, this whole thing should be what is called the, so this should be equal to delta JL. Okay. So, this is equal to 1 if j equal to L, equal to 0 if j is not equal to L. Okay. So, if this is satisfied, then you can immediately see that I can replace this whole thing by delta JL, and now when I sum over L equal to 1 to n, only the term where L equal to j will contribute. So, what I will get is nothing but sum over j equal to 1 to n xj xj. So, that is the only term that will contribute. So in other words, the condition for A to be orthogonal is exactly this. So, in order for A to be orthogonal, it must satisfy sum over k equal to 1 to n akj akl equal to delta jl. Okay. Now, what is this sum over k equal to 1 to n akj akl? That means what you are doing is you are taking the jth and lth column, okay, and the elements of the kth row, and you are multiplying them together. You should get 1 if j equal to L, and you should get 0 otherwise. So, in other words, what this says is that different rows or different columns of the matrix, if you think of one row of a matrix as a vector and another row of the matrix as another vector, then these two vectors should be orthogonal to each other. That is what you are saying. If they are orthogonal to each other, then you take a dot product of two different rows, you will get 0, and additionally if you take the length of any row or any column, you get 1. Okay. So, that is the meaning of this orthogonality of this matrix A. Okay. Now, additionally we can write this in a slightly more compact notation. So, instead of writing it in this way, okay, I can express orthogonality in a slightly different way. So, I can write orthogonality implies orthogonality can also be expressed as so I can write this as A transpose A. Okay, so A transpose is a matrix. When you multiply it by A, you get another matrix, and this product should be equal to the identity matrix. Okay, or you can write A transpose equal to A inverse. Okay. So this is the same thing as what we said here. Okay. So either you can say A transpose A equal to identity, or you can say A transpose equal to A inverse, or you can write this in terms of coefficients. Okay, akj akl sum over k should be equal to delta jl. So these are what it takes for a matrix to be orthogonal, and each of these three conditions are identical to each other. Now, so what I mentioned here is that the rows and columns should be orthogonal. Okay. So, in other words, if we said that sum over k equal to 1 to n AKJ AKL equal to delta KL. Okay, so what that means is that so if I take the jth column, then the elements of the jth column, so if you go to the jth column, okay, then the elements of the jth column are given as A1j, A2j up to ANJ, and then I take the lth column, then I will have A1L, A2L up to ANL. Okay. So now what you can see is that in this sum what is appearing is AKJ, and K goes from 1 to n. So, it comes A1j, A2j, A3j all the way, and then AKL, that is A1L, A2L up to this. So, what you are effectively doing is you are taking this vector and taking a dot product with this vector. So, essentially you are taking the dot product of these two vectors, okay, and that dot product should be 0 if you take two different columns. If you take the same column, that dot product should be 1. Okay. So, this is what you mean that any two columns are actually orthogonal to each other. So, columns are orthogonal. Okay. And similarly, I leave it as an exercise for you. You can also show rows are orthogonal. Okay. And more precisely, we should use the term orthonormal. Okay. So, orthonormal means it is not only a two rows orthogonal, but if you take a dot product of any column or any row with itself, you get 1. Okay. So, that means you can say AKJ sum over k equal to 1 to n. So, now I have taken L equal to j, this is equal to 1. You take the dot product of any row with itself, you take the norm of any row vector or column vector, you get 1. Okay. So, this is a property of orthogonal matrices, and what we have already seen is that orthogonal matrices play a very important role because any orthogonal matrix, when it acts on a vector, it gives a vector such that norm of y equal to norm of x. Okay, that is the so these orthogonal vectors have this norm preserving quality. Okay, and therefore now if you just think in terms of physical picture, okay, so this will look like a rotation. So, you say that you take a vector and you rotate it and you get another vector, okay, then the length is not changing, you are just rotating it, okay. So, the length is not changing, okay. So, a matrix that does this an orthogonal matrix is like a matrix of rotations, okay. So, like a matrix that rotates a vector, okay, and this is one of the most important applications of matrices, and we will see this in a subsequent class. Okay. Now, I will define a few more special matrices, okay, which you will encounter in various courses. One is what is called a Hermitian matrix. Okay. So, a Hermitian matrix is very much like a symmetric matrix. I think of this as the equivalent of a symmetric matrix for complex matrices. So, here we are not talking about matrices with elements which are real numbers, but we are talking about matrix whose elements are complex numbers. Okay. Then a Hermitian matrix. So, if this matrix has A equal to A, I will call it I will put a dagger sign. Okay. So, this dagger is what is called a Hermitian conjugate. okay. And what does it do? So, what does this dagger does? So A dagger is nothing but you take your matrix, okay, you take each element, you take its complex conjugate. So, this is a complex conjugate and then you transpose it. So, you do a transpose and you do a complex conjugate. So, you do both these operations, then you will get what is called A dagger, which is called a Hermitian conjugate. So, if a matrix is equal to its Hermitian conjugate, then you say the matrix is Hermitian. So, if A satisfies this relation, then A is said to be Hermitian. Okay. So, you can clearly see that this is like a symmetric matrix. So, it is like a transpose, but you do not just stop at transpose, you also take a complex conjugate. Okay. So, it is like the equivalent of a symmetric matrix for a complex matrix. Okay. And this is Hermitian matrices are again these are very essential part of quantum mechanics. The Hermitian property of various operators, okay, is a very essential part of quantum mechanics. Okay. There are some nice properties of Hermitian matrices. Okay. So, Hermitian matrices have real eigenvalues and orthogonal eigenvectors. So, this is, so if you take any two eigenvectors for two different eigenvalues, they will be orthogonal to each other, and eigenvalues of a Hermitian matrix are strictly real, they cannot be complex. So, in fact, this is part of the foundations of quantum mechanics, where you invoke Hermitian property for all operators that correspond to real observables. Okay. Just for completeness, I will tell what is a unitary matrix. So, a unitary matrix is like an orthogonal matrix for a complex matrix. So, it is like an orthogonal complex matrix. So, remember, in orthogonal matrix you had A transpose equal to A inverse. Okay. Now, what you will do for a unitary matrix is you will take a transpose and you will take a complex conjugate. Okay. So, A inverse equal to A dagger. Okay. So, this is what is meant by unitary matrix. So, if A satisfies this condition, then it is said to be unitary matrix, and so you can think of a unitary matrix as the equivalent of an orthogonal matrix for a complex space. Okay. And so a unitary transformation is something that will, when you operate a unitary matrix on a vector or another matrix, you will get something that preserves the norm of the vector. Okay. So this is norm preserving in complex vector space. So, if you are having a complex vector space, okay, then the norm incidentally also involves the complex conjugate. It is not just a simple dot product, but you also have to take a complex conjugate, and the unitary matrix is a matrix that preserves the norm of this vector during a transformation. Okay. So, this is what I want to say about unitary matrix. Okay. Now, I will just mention briefly that there is something called similarity transformations. Okay. So, suppose you have a matrix A. Okay. Now, you can take this matrix A and you can transform it to A tilde. Okay. And there are several ways to do this transformation. Okay. So, one way to do this transformation is you essentially you take A and you can, I'll just write this. Okay. Okay. So suppose you take S A S transpose. Okay. So, S is a, so I am just taking some matrix, okay, some matrix A, okay, and I am doing S A S transpose. This is called a similarity transformation. Okay. So, one very common transformation that is used in quantum mechanics is called a unitary transformation. So, what you do is you take A tilde equal to U A U dagger, where U is a unitary matrix. So, this is called a unitary transformation. Okay. So, you do this transformation using a matrix U. Okay. So, such transformations of matrices are often used to change from one coordinate system to another. So, I will stop the lecture here. Okay. So, in the next class we will talk more about we'll talk about matrix diagonalization, spectral decomposition, and then in the last class of this module we will do some practice problems. Thank you.